Hello everyone, welcome to today's webinar for Adapt software. My name is Spencer Lee. I'll be doing the training today, and today we're going to be talking about modeling, analysis, and design of a two-way RC slab in Adapt Builder. Specifically, we're going to be using Adapt Floor Pro for the design and the modeling. And just a few announcements before we start. This video will be recorded and the webinar will be placed on our YouTube channel. You can reach that at www.youtube.com/adaptsupport. If questions are unable to be answered today, or if we just run over time, feel free to contact us at support@adaptsoft.com. We'd be happy to answer any questions. If any of you would like the training material, the model, both the Revit model and also the Builder model, along with some supporting documentation, feel free to contact us also, and we'd be happy to send that over. So we're gonna go ahead and get started. If you have questions, if you can, please reserve those to the end of the training. Just take a note, and I'd be happy to answer questions in a Q&A after the presentation. That allows us to get through the material and just have a flow of the material. So the best way to ask the questions within the GoToMeeting panel that you should see on your side, there's a questions block that you can go ahead and write the questions in, and then we can take care of those afterwards. Everyone should be able to see the screen. If you cannot, please let me know. And what we're going to be doing today, we'll just go through a quick summary. We're going to be talking about a two-way RC slab in Adapt Builder. We're going to go through just a modeling process of this, essentially integrating a Revit model and bringing that into Adapt Builder. We're going to talk about just basic loads, combinations, load cases, and we're going to touch on skip loading. We're not going to use skip loading in the material, but we will show just a very brief example of how that can be handled. We do have tutorial videos related to several of the things that we're going to talk about at the YouTube channel that I mentioned earlier. So you can always access those videos on demand at your convenience. We'll talk a little bit about design assumptions and criteria, and also design strip creation. How do we model column strips? How does the program handle middle strips? And how do we classify those design strips when we're designing them in terms of a design type? Is it a two-way slab, a one-way slab, a beam? So a lot of that can become very detailed in the program. We want to talk about how those settings can be made up for those design strips. And then we'll talk a little bit about meshing, analyze the model rather, and then we'll go into some results: punching shear, deflections. How do we treat deflections, both for just immediate deflections, linear, elastic solutions in terms of the deflection? How does the program handle crack deflection, long-term deflection? We'll talk about the actions, moments, shears, etc. at sections, and how we can investigate the design strips. So everything will be predicated on layout of design strips using nodal integration and obtaining the forces and actions in those strips. And then finally, we'll end with reinforcement and generating rebar and being able to use that information and export that back to Revit or in a DWG format. So that's what we're going to try and cover today. We have about an hour, and we're going to go ahead and get started with the actual process here. We're going to be looking at this model. I'll go ahead and just give a brief overview. This model may look familiar to some of you if you've ever gone through our written documentation, which is, we have a written tutorial that essentially is this model. It's been tweaked a little bit at this first floor to make it, I think, more conducive to have a mixture of beams and slabs. So we want to talk about how we can combine both types of elements in the program in terms of a design. We're going to use the Adapt Revit link to take this model, export it from Revit to Adapt. I'm using Revit 2020. We have Adapt Revit links from Revit 2006 all the way through 2020. Soon we'll have the 2021 Revit link. And We're going to be using the latest version of Builder. This is actually Builder 2019.1. I'm using an internal version, so if you've been using Builder and you see something a little bit different that I'll show you, don't worry, that's going to be released likely within the next 2 to 3 weeks, and that includes the addition of a property grid. So it maybe look a little bit different from my end versus your end, but we'll go ahead and I'll just note where that difference occurs. So first, we're going to take this model and we're going to use the adapt plugin here. We're going to export the model as an IMP file. So if you have custom parameters for column types within Revit, you may have to map those parameters here. We're going to just use the default parameters. The program has a few dialog windows that allow you to see some of the information being exported from Revit to adapt. We'll just use the defaults here. We're not going to explore this in much detail. I'll just go ahead and export the data. We're going to save this file. This is an IMP file. This is the adapt, I'll call it the typical adapt or the adapt neutral file. It's just our native file that we use to write data through different platforms. We use it for transfer of information from other softwares, Revit, eTabs, Tekla Structural Designer, and others. It's also used internally. So if you have a builder model that you want to share with another user, you could always export an IMP file, import that into Builder, and just create a new file off of that IMP file. So let's go now and let's open Builder. Inside of the Builder splash screen, we want to make sure we select the right programs or modules that we're going to use for this analysis. We're not going to do any lateral analysis for a global or multi-level model today. We're kind of sticking within the realm of just basic gravity RC design. So we're mainly going to be using what we call single level mode, and I'll differentiate the two. It's an important differentiation when you start using the interface and you begin modeling, and not only modeling but also analyzing a structure in the program. It becomes important to understand and recognize what mode you're in. So we're going to turn off Edge. Edge is really our frame solver. If we had a 20-story structure and we needed to analyze this both for lateral gravity loads, we would need Edge in order to analyze that. So Floor Pro gives us the ability to simply analyze one single level at a time. And we're going to stick in the Floor Pro realm today. We're going to be using we're going to be using the RC mode. This is differentiated against the PTRC mode, which would give you the ability to design and add post-tensioning. It could be unbonded or bonded post-tensioning. This just opens up a new world of possibilities with the post-tensioning tools within the software. So we'll stick with RC today. We do have a seminar or webinar coming up in a couple of weeks that is a two-way post-tension slab. So some of you may have signed up for that. We're going to cover the PT part of this 2 weeks from now. So modules, we're going to go ahead and ignore these. These really allow the user to integrate with our 2D software, which is called Adapt PTRC, and also the PT Shop / Felt 3D. This allows you to calculate losses, short and long-term losses for post-tensioning within the modeling environment when you enable this PTRC mode. So today we're going to be working in US units. We'll go ahead and we're going to start by importing the file from Revit. So there's a few different options here. We could also import a CAD file, and I am going to use this for one thing within this model that we're looking at. So I'll go ahead and use the IMP option. I'm going to open up this M1 IMP, and we want to go ahead and create a brand new model for this example. We could import just one level, or we could import the entire structure. Maybe we want to keep all those levels together within the same modeling environment and the same model file. So we'll import the entire building. If you do choose to go to one level, you'll notice this becomes active, and you can go ahead and filter out different component types that you may or may not want to include in that file. This may be used more in terms of being able to update an existing model if the columns or walls change location, you may have to re-import a Revit file and update. So this is useful for that purpose. We have no load cases or combinations defined in that IMP file from Revit, so we're going to build some of that inside of Builder. We'll select OK, and you'll notice that first thing to note is we are looking obviously at a plan view, but we're working, it automatically enables multi-level mode. So if I go to a 3D view, you can see all of the floors brought in from Revit. We're really going to just focus on level 1, so I want to make sure I switch over to single level mode, and I'll just navigate here to level 1. And here we have level 1. Now when I go ahead and analyze the structure, if I mesh, analyze, get things set up, when I analyze, it's only analyzing what you see in single level mode. So the program will auto restrain, add supports at the bottom of these columns and walls, and those supports are based on whatever the settings are set at inside of criteria, analysis, and design options. We have different support settings depending on which mode you're working in, single level or multi-level. The single level default condition is a roller. It's really a fixed roller. We release the X and Y translational restraints. And for multi-level, we just assume fixed. So the user has complete control over this. We can modify based on whatever our support conditions are. The default out of the box is what is shown here. So if I was to analyze the structure, again, it would use a single level. If I go to multi-level, the program automatically deletes any automatically generated supports at level 1. For example, let me go back to level 1 here, and I'm going to go to model, and I'm just going to create the supports. You can see the program creates a support at the base of the structure. If I double click on that to look at its properties, these are the properties per default. The upper columns, we actually release all translational restraint here. Again, this is the default. If I switch to multi-level, I'm actually still seeing the supports at this. This is actually level 2. Okay, so these supports remain there until we go back and we analyze this in multi-level mode. The program essentially erases the supports and restabilizes the structure at the base as a fixed condition. So that's how it handles the supports in the different modes that we're working in. That's important to note. If you actually make a user modification, if I, for example, say, well, I want this to be a hanger, so I want to go ahead and fix in the Z direction. Once I make that user modification and I switch back into multi-level mode and I rerun, that user modified support is retained until I remove it. So sometimes you may catch yourself in that that mistake if you don't remember and you don't automatically remove that support. Okay, and I'm going to go ahead and just delete that. I don't know that I changed it, but anyway, we'll go back to single level. I'll go to my default view, and we now have a model. Now, by default, the program uses the concrete assignments inside of Builder. So if we check under criteria, concrete, you can see this is defaulted to concrete 1. The compressive strength here is set to 4,000. We're just going to leave the default properties alone. If you need to add more concrete materials, you can always select add, and obviously that populates that. You can make changes per selection in this window here. Under the design code, by default, since I opened in US units, the default design code is ACI 14, IBC 2015. One distinction to note is when you open the program in RC only mode, you have the ability here to produce probable crack widths. So I could show the crack widths in the slab. I could actually limit the crack widths in the slab. The program, in this case, utilizes European code methodology and some of the requirements there for adding reinforcement to limit crack width. So we calculate the crack widths. If you choose to limit the crack widths, you may end up with additional reinforcement other than what's mainly common for ACI, which might be just temperature shrinkage for for a 2A slab like this. So we're going to report crack widths. We're not going to limit crack widths in this example. We'll go ahead and select OK there. I'm going to go ahead and save the file. So we'll just file, save as. Okay. The next thing we want to do is look at loading and load cases. Now, by default, under loading, there's a few reserved load cases. The program will auto-calculate the self-weight of the members, so we don't have to worry about the self-weight typically. Under the general loads, we're going to mainly be working in this realm under general. This is where we would add additional gravity load types, snow load, roof live load. Maybe there's mechanical loading. And we have a superimposed dead load and a live load just as default loads. We're going to use those today. Building loads is something different. So if we use our wind load wizard or our seismic load wizards to generate loads on the global structure, and I'll go back to this view here, and I'll go back to multi-level. So let's say we have a set of forces that are produced at each level just based on static lateral method for seismic, for example. These forces are generated through either the seismic load wizard or through a generic input where we actually enter the loads in this table, and we call this, let's say, EQX, for example. So depending on where you enter these lateral loads, whether it's wind, seismic, or lateral, these are classified as building loads, and building loads are only solved for when we are working in global mode. So if I add a series of building loads here, seismic loads, and I go to a single level, this particular force here will not actually be considered on this level in single level mode. So we want to stay away, and when we're working in single level for maybe a gravity design, we're staying away from the inclusion of building loads in this realm. We are going to cover the application of wind loads and seismic loads in a webinar. I believe it's on May 9th. You may have to check the schedule that I've sent out to many of you. But we're going to talk about building loads and lateral analysis in the program. So just make sure when you enter loads that are intended for gravity application, you use this general load input. Now, you may be confused, well, why does this say lateral? If you just showed us lateral, this also specifies lateral. This is actually used for a situation if you had, let's say, a podium slab. Maybe there's a parking, this is P1, and this might be podium. And we have a timber structure on top of this podium slab. Obviously, the platform doesn't handle wood design or wood analysis, so we have to somehow get the reactions out of this timber structure and dump them onto this podium level. Those reactions, whether they're in the form of lateral loads in the X or Y plane, maybe they're in the form of force couples at shear walls, maybe you have point loads that are force couples for overturning and so on for shear walls. Those types of reaction loads from a externally applied set of shear walls or an externally applied building, those would be classified here as lateral loads, because we may need to run that podium in single level mode, but we may have to consider those up and down force couples from the lateral analysis of an external building that's not included within the model. So those are reserved for, again, the general load case. Okay, so those are the load cases. Let's go ahead and look at combinations. By default, we have just a few combinations based on the code that's been selected. So this is centric to gravity loads. We have 2 service loads, 2 sustain load, or 2 strength loads, and the user can always, if you build this out to include more load combinations, you have a few possibilities. One, you can always save this model as an IMP file, export it, and then import it into another model and only import the combinations. So if I built 500 combinations, I could import those into this model through IMP. I could also save the file as a template file. So you could save this as a project template, include criteria, material, combinations, and then you could call that template file whenever we create a new model and use the template save data or input for that model that is using the template file. So there's a few ways to save time, be efficient without having to rewrite combinations in every single model that you're working on. There are tags associated with the combinations, and these dictate how the combination is handled in terms of reinforcement or no reinforcement. So if we evaluate a service combination, if we have service sustained or total, this is more in tune, I think, with post-tensioning design, where we're checking stresses under those conditions. And depending on the stress level, and for example, positive bending regions, we may have more reinforcement for minimum requirements, so for a PT slab than we would for an RC slab. So for service combinations, we essentially calculate minimum reinforcement. If you look at a design strip in this slab, and I look at the reinforcement required for service total versus service sustained, it's independent of stress level. It's independent of the actual service level actions in the section at this particular combination state. In other words, for both of these combinations, the program would just calculate minimum area of steel for temperature and shrinkage for an RC 2A beam, or RC 2A slab rather. For a beam element, we check minimum flexural reinforcement, for example, under the service condition. For a strength combination, we actually calculate the reinforcement needed to meet the demand moments, the ultimate moments at any design cut. So if we don't add any base reinforcement or user reinforcement in the model, then we essentially rely on the program to calculate the reinforcement needed so that we have a demand capacity ratio of less than or equal to 1. So that's how the strength combinations are handled. Crack deflection is a special analysis option type that allows the program to check that particular set of loads under those load factors for cracking. So for example, if I use this option down here, there's another type called long-term deflection. I'll talk about that in a moment. And then also P delta. P delta we'll get into in the lateral webinar. We're not going to use that here, obviously. No code check just simply allows you to produce a solution for a combination, and you can then review results for that solution, but there's no reinforcement designed for no code check. There's actually no reinforcement designed for crack deflection. It just utilizes the reinforcement that's been designed for these other combinations when we go through and we solve the crack deflection in the software. We're going to add this here. We're going to go ahead and we're going to assign a creep and shrinkage factor. We'll just assume this is 2. This is similar to the requirement in ACI. I don't know if I'd call it a requirement, but it's a suggested long-term factor for concrete structures there in ACI 318. So we're assuming this is in service maybe 5 years out, and the creep and shrinkage factor here is 2. We'll go ahead and select that, and the program is going to add 2 combinations by default. It adds sustained load. This is actually set to a cracked deflection analysis type, so the program will produce a result for this load combination for cracking. And then the long term is really just the deflection, the immediate deflection due to the sustained plus the creep factor. So we get a factor here of 3 times sustained. And this is just a very quick shortcut into entering a couple of combinations here. I could actually enter it multiple times and get different sequential combinations built, but they're always producing the sustained load. The user has the power, the ability to generate really any set of cracked combinations and long-term combinations in the software. So long-term really gives you the ability just to combine the solution of other combinations, whether they're cracked, strength, no code check. This just references other combinations to create an envelope of, if you will, of those combinations inside of this entry with an appropriate factor, whatever you deem that to be. So we're going to run the model for these combinations. We'll look at cracking just in a simple example here, and then the long term. going to go ahead and we're going to add some loads. So the loading in the program is always cumulative. You can add loads in either direction, positive, negative, relative to the global axis orientation. We're going to use what we call load mapping. We're going to map the loads using this wizard. So I'll just select my slabs. For this example, I'll use 20 PSF dead load, and I'll use 40 PSF live load, but we're going to add an additional 60 out on the balcony and in this region here for, we're going to say this is an assembly area here. Maybe it requires 100 PSF total. So I'll go ahead and I'll use the patch load wizard. This is just going to map the load directly to the selected slabs. And let's do dead load first. This is in KSF, so 0.02 KSF. And I'll come back and just re-enter this as 0.0, let's say 4. You'll notice if I switch views here, we get something like so. Now, because this balcony already has 40 PSF live load, I'm going to add an additional 60 to get my 100 in that region. So we'll say 0.06. Okay, and then I don't really have a slab to map load. I'm going to put 100 PSF in this area also. So I already have 40 here. Since I don't have a slab that I can map it to, that's fine. I'll just use my regular input of uniform or patch load. And we're going to use my snap tools and try to put this in the proper region. So we'll go down to there. I'm not going to get too specific with the placement. So there's our load. And if I double click on that entry, I can then change that to my desired magnitude. Okay, so that's my loading. You'll notice if you use this visibility panel, you can then kind of control what loads are shown, point, line, patch, and I can go further and drill down into filtering out what those loads are associated with, what load cases, dead, live. I could turn on dimensions, which would show magnitude, for example. I'll do dimensions here. If you don't like the height of that symbol, we can control that here just by using the symbol size. I might change that to 5. And then we have our magnitudes. You could also produce a graphical, kind of a hatched view of the loading under the load reports. We can go to graphical reports, live load, and this would show us a different type of view where it's just hatching the load region. Okay, so the loading is fairly simple. You can map line loads and patch loads to slab regions. You can also just generally, enter those loads through this application of point, line, or patch. So one thing to watch out for is if you have a slab setup where you have nested slabs. So let me go ahead and show an example here. If I put a slab inside of this slab, I'm going to change the slab thickness here to 10 inches. And I'm going to use, here I'll use a 9-inch slab, and we're going to use a 1-inch offset. So the vertical offset positive is downward. If I take a section cut under my visibility panel through this section, you can see there's my beam. Here's my little step, that 1-inch step into a balcony for that location. Now here I'm actually going to say I want to have a 12, or let's say a 13-inch slab, and I want a 2-inch offset. And if I take a section through that location, you can see there's that depression right there. So the program knows how to handle those slabs that are nested inside of each other. Something that you have to watch out for is the mapping of those loads. So had I originally had this slab prior to me mapping the live load, for example, and I select all of my regions, maybe I select this one also, and I go and I map this with 40, what you have is you have 40 around here, but I also have 40 here. So now this ends up being 80. And that may not be what the user wants. They may only want 40 even over the depressed area in this example. So just be careful when you're modeling nested slabs and mapping loads to those slabs for that double counting of the load based on the selection of the slab. Okay, the next thing we will look at is skip loading. And we're going to use just the fully loaded floor, but I do want to show an example of skip loading. I actually just put a video up on our YouTube channel related to this topic that has more detail. But in order to pattern live load in the software, we have to first generate what we call subregions. So I'll just generate subregions based on these dividing lines. We can really just say polylines that we're going to add on the slab. This divides it up into some set of these intersecting zones. Okay, and let's do one more here. And then in this direction, I'll go ahead and just cut this across here. So we have 3 divisions this way, maybe 5 or 6 in the other way. And now I'll go to load patterns. And this allows us then to define the load case that we want to use in the skip regions. We can choose to reduce the live load, or the selected load rather, in that region, and then apply a skip factor. So if I want to select first all of my combos, I'll add that as a pattern. Maybe I just want to select this row as a pattern. I'll do alternating regions here as a pattern, and maybe the middle bay here as my 4th pattern. So we can create multiple patterns using this tool. Those patterns then get dumped into this dialog. So you can see patterns 1 through 4. Those can then be associated with a combination. And the envelope of patterns, max, min, are also included here and here. And I would recommend, if you're interested in this feature, I would go to that video posted today about load patterning, because there's a clear distinction made between when you should really use the max, min skip values or skip results versus individual pattern results. If I had to generate a combination for, let's say, a set of combinations for each pattern, for each one of these patterns, I would have multiple clones of, for example, service total. I would have 4 here, and I would add a factor 1, 2, 3, 4, and then I would repeat that for sustained. That might also be 1, 2, 3, 4. And this is required when we're actually designing design strips in the program, and it's based on how we handle the nodal integration when we design those sections for the slab. So that video has much more detail on that particular process, but I just wanted to kind of give you a flavor of how you would set the patterns up at least, and use that within the context of a slab design. So I'm going to go back just to avoid any mistakes. I'll go back and I'll just delete out those patterns for this example. I'm also going to delete the subregions, so we'll go to select by type, subregion, delete those. Okay. All right. One of the most critical aspects of obtaining a design in any slab, whether it's PT, RC, with or without beams, is the ability to generate design strips. So we could go and mesh this slab and analyze the slab and get what I call raw or just basic FEM results for the slabs. We could get deflection contours, frame actions, shell actions, etc. But we need the capability of actually designing certain regions of the floor or the entire floor for reinforcement. I want to know what the moment is, for example, maybe at a column strip at the face of support. I want to know what the moment is along this path, at the positive bending region between these 2 columns. So in order to invoke that, we have to generate design strips. And those strips are what we use to evaluate the floor, whether it's an RC 2-way slab, an RC 1-way slab, a beam, with or without PT, we have to generate strips. So this is one of the fundamental things, not only in this software, but most software that you see that handles design of slabs. You're going to see some form of generating design strips. So in Adapt, there's a couple of ways to do this. For those of you who have used Adapt in the past, there were some improvements made between version 2019 and the versions prior to that, where we loosened up the requirements of these these components that we call splitters. So I'll talk a little bit about splitters, but we're going to show you how we can go about modeling the design strips. I could go in and I could just basically manually create the design strips. So for example, if I want to create strips in the X direction, I'll do the column strips or the beam strips first. And you'll notice a lot of times I'll actually snap outside the slab boundary, because I simply don't like to zoom in and zoom back out when I'm working with strips. So I'll go ahead and I'll just snap out here, and I'm going to snap at the endpoints of beams, and I'll close that off at the slab edge. Okay, and we'll do something similar. I'm going to assume that this is a middle strip that flows into a beam and then flows out back into a middle strip. So we'll go ahead and I'll snap there, I'll enter. That's going to be designated as a two-way slab. This will be designated as a beam. And then we have, again, a two-way slab. Okay, on this side, this will be purely a beam strip here. And another option would be to use a dynamic editor. So I could go in and just use this X and Y wizard. This allows me to use a construction line. So if I go in and I just pass this through all columns, enter, the program picks up the points on that intersecting line with the columns. And notice that for the beam, it doesn't really differentiate between the beam and the two-way slab here. If you double click on this support line and go to the design settings, it says two-way slab. Technically, the program can handle the design of the beam requirements in this setting. However, I'm going to show you a different approach to handling this. So one thing you can do is if you snap near the endpoints of each beam segment, I'm having to snap 1, 2, 3 because I have a beam segment. This is beam segment, I'll label this. This is 1 and this is 2. There's a break right there between the two. So they're actually two separate beams in this case. And if I snap near the endpoint here, and then I go all the way through, you'll notice now that the program breaks this. So this is a two-way slab, and this now becomes a beam criteria here, and also a beam criteria there. Now, one thing you have to deal with in this case, because my beams are modeled away from the slab edge, it actually creates a tiny little support line even here. This is considered two-way. There are no real adverse issues with this. It's a little bit annoying just because you have to deal with it. Had that beam been modeled out to face, I wouldn't have that segment. So keep that in mind. I'm actually going to just delete it out so we don't have to deal with that. If I manually created this, I also wouldn't model that tiny little segment in that zone. So let's go back and continue on. We'll go ahead and snap near the endpoints of walls to pick those up as supports on both ends. And then here we're going to go ahead and just chain this to create my beam segments for each one of these beams. Okay, if we want middle strips, the program does not have an automated middle strip generator. I think for the most part, when you insert a support line between two column lines, the middle strip and the integration of those is very, very close to what you would get in the outcome of just hard calculating the distance, let's say half the distance centered in this strip, for example, or in this bay. So in this case, I'm just going to go ahead and model middle strips based on the location where I think they should be. Okay, so that we'll go ahead and I'm going to model a middle strip there. We already have this middle strip here. You know, you could model another strip here. I'll just leave it as is, and then down here we're going to model a strip along this path. So I'll just do 2 points that passes through that location. I'm going to close this. And if we wanted to clean up these points on the perimeter, I could always just bring those back to face of slab. We don't need to, but just for sake of cleanliness in terms of the model, we'll go back and adjust those. I could adjust these back to the face of the openings. Okay. And if we wanted to make sure that the strips don't encroach into openings, then I'll use a splitter. So I want to use an X direction splitter. I don't want the program to extend the design cut, for example, here down into this opening. Technically, there's nothing wrong about that in terms of just the result, the pure result. The program doesn't see any elements in this zone anyway, so it can't integrate over an element where there are no nodes. But again, from just a kind of a cleanliness of modeling standpoint, you may not want to see those section cuts passing through. So that's fine. We'll go ahead and add some boundaries. The program will stop the section at that boundary. Even like here, if I create that boundary and this boundary, now nothing, there will be no cuts that extend through from this inner support line. I likely wouldn't actually add that support line in between there. It's just the slab over the top of a wall. But for sake of efficiency in the meeting, I went through that location. So here we're going to add a splitter, and then again a splitter there. We'll do one along this boundary also. Okay. And in this case, we have a section cut. If we have that balcony here, so I may not want that balcony to be part of my beam section. If you don't, then we could always add a splitter there. So I might say, well, I want that splitter really to be on that zone. And then that means I would have to add an additional support line along this path to get design cuts in that balcony. Most of the action is one way, bending about the global X axis here, but we may want to see what's happening along the transverse path in that balcony. So if I go ahead and generate the cuts, these are my strips now for this direction. If you double click again on the support line, you can designate under options, you can designate how many sections you want, what's the spacing you want, how many sections per span. So a span is defined as the distance between 2 points on the support line. For beams, if we look at this beam here, we may want the program to actually use the effective flange width when I calculate the reinforcement. When I evaluate the section for reinforcement, we may not want to use the modeled or the physical flange. We may want to use the effective flange. So this allows me to enable that for beams, for beam design. So these are my strips for the X direction. I'll go ahead and just delete those. I'll control their visibility over here in this visibility block. I'll just turn them off, splitters and support lines, and we're going to do the same process here in the Y direction. I'll try to work through this a little bit faster in this direction. A lot of times the layout of these is very subjective in terms of the user. We're trying to just define the load path, and clearly this slab has a nice layout where the load path is pretty easily definable. There are times where you have load paths that are not as easily definable, so that sometimes presents a challenge. If I wanted to use the editor again, I could come back to this if needed. And maybe I want to add a middle strip here. So I would might add that as a middle strip. Notice it actually just takes this point and this point. And what we could clean that up, I probably would go back to using this manual input there on that one. Let's do that. So we may bend that and then bring that straight up like so. Here we'll go ahead and okay, and I'll come back to the editor again, Y direction. Make sure you toggle to the right direction there. Okay, and then we'll do one more here where we have beams. So we want to make sure we snap near the endpoints of those beams. Same thing here. This will just be middle strip with a beam down on the bottom. You can see we'll have to clean that up. It created some strange looking support line at the bottom. That's not a problem. We'll easily be able to handle that and take care of that. And then we have this one. So I'll close that. And we're going to go ahead and I'm going to get rid of this one, and then I'll go ahead and extend that out. Usually we have some level of cleanup to do on these strips. This one I'll straighten perpendicular, and then over here we have this strange little jog in the slab. We'll just delete and extend that back down. Okay, and let's add one more along this wall right there. And we're going to go back and now add our splitters, our boundaries. So we'll add a boundary on this opening face. I'll add a boundary on that opening face. Do the inside here. We don't want that to cross into that opening space. Same thing there, same thing there. And these become our column and middle strips, for example, for this direction. I might want another strip here. And then again, we could come back and drag those back to the slab edge. Try to keep the same standard of excellence here for the layout. So let's go ahead and generate the strips. Now you'll notice this says it found one strip with less than 2 design cuts, support line 34. So I could select by type, support line 34, and figure out what's going on there. We have a tiny little strip up here. That's that strip that gets added to the end of the beam. So if we don't want to that issue, it's really something we can ignore, but I may want to just extend that up and then go back, regenerate the design cuts. And I have now my cuts in the X direction, X and Y. So these are going to be our strips for this slab. Okay. We're now going to go ahead and analyze the slab. So we've set the model up. There are additional settings and criteria settings that the user may need to pay attention to. I would recommend you go through these in detail. We do have a documentation up here in the help menu. There's a series of documents. There is one option here, or one document that describes everything in the design options. So everything you see here, which kind of affects the analysis and the design, that's indicated in this document. I would read through that. It's only 2 or 3 pages. It just gives a brief definition of those settings. If we wanted to account for twisting moments using wood armor method, there's that option. We can also check reinforcement to be larger than cracking moments. So this, in essence, becomes a new combination where we produce reinforcement greater or to meet the demand moment equal to 1.2 times MCR. That's another option. If you add reinforcement, maybe the user wants to add base reinforcement to the model, then you have the ability to just turn off the addition of minimum reinforcement. You may have already added it in terms of like a bottom and top mat, and the user can ignore or suppress the addition of base or of minimum reinforcement. So let's say I wanted to add a mat to this slab. I could go to rebar. I could just use Mesh Wizard and go in and say I want to use number 5s at 12 both ways. 5s at 12 both ways, and we define the cover and the placement of that top or bottom mat. This is a bottom mat. It's indicated by the red color. That's the default for bottom. Green would be default for top. And now we have a mat inside of the slab in this location. If you generate a mat, let's say that this mat actually encompassed not only this slab, but it actually went out to the balcony as well. This would not be an issue for the bottom because you have the bottom is flush. If I added a top mat in this entire zone and the top mat was only offset maybe by 1 inch, that top mat would actually be on top. It would be at the actual slab surface of the balcony. So my recommendation is if you add base reinforcement in terms of mesh reinforcement, add it to each individual slab zone. Then the program knows to offset from this slab, slab 1, and offset separately from this slab, which is the balcony slab 2. That's the proper way to add the mesh reinforcement in the program. You could also add banded rebar. So I could add, reinforcement at any location. I can designate properties for that rebar, top or bottom, cover, size, spacing, number of bars, length of bar, and so on. You could also do distributed user-defined rebar. Maybe I want a bar here that goes from end to end, and I want these spaced at 12 inches on center. So we could go ahead and fix the spacing as 12. I'll unfix the number of bars and just update, and the program fills in the number of bars over that zone. This is all then accounted for when we calculate crack deflection. It's accounted for when we generate the design of the strips, whether it be for minimum reinforcement or for strength reinforcement. So this is user-defined rebar. We're going to say there's no rebar in the model. I'm going to go ahead and mesh the slab. So I'll mesh to the default sizing. This is just a simplified mesh. It's a sparse mesh. So you can see the components are pretty well shaped in terms of their aspect ratio. We don't have a lot of elongated shells, which could be a problem and cause a lot of distortion in the solution for those shells. But if you wanted to go to a uniform shell, we just switch over to uniform. Advanced meshing only really applies where we have walls. If you have walls with openings, then we might go to the advanced mesher. Then we can mesh walls and slabs using separate sizing. We're going to just use simplified. And if I go to a uniform mesh, now this gets tightened up a bit in order to maintain some threshold for the aspect ratio for the A and B side of the shell elements in this mesh. So I'm going to go back to sparse just for sake of time in terms of solving this, and we're going to run the analysis. So I'll execute the analysis. This block over here, really, we're not going to pay any attention to that. That's meant to combine, let's say, reactions from a global analysis into a single level analysis. If I, for example, am designing a foundation system in the program and I have a 20-story building on a mat or a raft slab, and we want to solve that model globally and then dump those reactions onto the mat, we would be using some of these tools here. And that will be covered a little bit in that lateral analysis webinar in a couple of weeks or in a few weeks. We're going to focus mainly on this input here. So one thing to note is by default, the program uses this usage case, which we call uncracked. That just means that we have not assumed any of our elements be cracked, or we have not reduced stiffness for any elements in the model. So the user has the ability to add what we call usage cases, and I'll just show an example of that. If I double click on a slab, for example, and I edit the usage, I could go in and drop in, 3 or 4 or 5 usage cases with different levels of stiffness modification. So I'll just call this cracked, for example. Once I define the usage case, then I can change the assignments. Let me turn off the shell elements there. I could go in and modify the stiffness for that one usage case. Uncracked is read-only, we can't modify it. If I want to modify the stiffness of all of my beams or all of my columns at one time, I could just select those elements by type. Maybe I want to do the beams, and we can modify that selection under the beam stiffness. So this modifies all of those at the same time. And we would set up those usage cases, and then when we go to run the analysis, we can choose which usage case. I call it a stiffness profile that we want to use for that particular analysis run. We're going to use uncracked. I'll go ahead, select OK, and we'll run the analysis here. We're quickly running out of time, so I appreciate everyone's attendance, and if you need to leave, I know it's pushing on 1 hour now, just don't hesitate to exit the meeting, but we'll continue on here for probably another 10 minutes or so. We'll save the analysis. Now, once you've saved the analysis, the result browser will open over on the right-hand side. You'll see that browser here. The browser allows you to select the load combination or envelope of classifications of combinations, for example, envelope of service or envelope of strength, in order to produce a result. So if I wanted to look at the deflection due to service total, I could just go into slab, produce my deflection contour. You can change the display of the view here. I could increase the text size, for example, for this contour text under just general text settings. That is unreadable, so I'll change that to 22, for example. I'll just double it. We could also change the number of contours, so this allows us to kind of increase contours. The presentation of the contours can be controlled under settings. Maybe I want that to go to a fixed range of color, and so that changes the presentation of the contour. So there's a lot of different settings here. You could change units and so on. Unit system, if you wanted to actually show this in metric, but you modeled in US, you could toggle the unit system here. Notice there's some duplication here. I'm using the internal version of 19, and you'll notice here there's a property grid. That's the thing that I mentioned in the beginning of the webinar that's up and coming. I'm actually going to turn that off. When I turn that off, this is what the current commercial version looks like. So you don't have that property grid yet in the versions that you're using. Back to analysis, we can produce any contour relevant to the shell element results. We could also produce frame element results. If I wanted to take a look at the column axial forces based on this run, then I could graphically turn those axial forces on. I could turn on moments and so on. So this is just a view of maybe raw analytical results. Our main objective here is to design the strips. I want to know what's happening with the reinforcement and the bending, maybe in the slab and even the punching shear. So for punching shear, before we actually generate the strips, I would run over here to floor design. I would set up my shear design options. We're going to go through and set up our two-way shear options. I'm not going to spend time defining everything. We'll just leave these as is. We do have videos related to this and documentation, so you may want to check that out for further information, but we'll just leave those as default, and I'll execute the punching shear check. Once I've executed that check, it's really only made for strength level combinations. So if I come back to envelope of strength, run over here to analysis, I can collapse that maybe and go to punching shear. This gets automatically updated when we make a run of a particular design type, punching shear or processing the design sections. Whichever option we choose and whichever option we run, this gets updated. So now I'll check the stress check. Notice that there's one column here that requires reinforcement. All others are okay or not applicable. Any column that is connected to a beam is actually not checked for punching shear. As a trick, what you could do before you actually run the punching shear, I could actually select these beams, for example. I could disregard them. And if I run punching shear again, the program should actually check that now. So that's a way to check columns when beams are connected without having to live with the constraints that the program puts on you. You can trick things. So we'll go ahead and consider that again and run punching. Updates that. So stress ratio can be shown graphically. Condition, this kind of shows you how we're checking the column, whether it's a 3-sided, 2-sided, or 4-sided condition in terms of its critical section. And then ultimately we get this output for reinforcement here for the stud rails. This is kind of a shorthand, abstract way of generating that reinforcement output. This means you have 2 rails. 8 total rails. So you have 2 rails on the R and S sides of the column, and you have 8 studs at 2 inches on center on each rail. Okay, that's how that should be interpreted. And then you have the option to go to reports. Under punching shear, we can just produce a punching shear report. This is actually an Excel file that just dumps all of the numerical data out for you for the punching shear checks. It's pretty exciting if you're into numbers. If you're not into numbers, then it may not be as exciting, but you can also produce, for example, the punching shear reinforcement schedule. So here we're just going to have one entry, and the this shows that one column ID, number of rails per side, and gives information on the design of that one column. So that's just a quick show of the punching shear. Let's go ahead now and generate our design cuts. Now, if you want to investigate sections, meaning you don't want the program to add any reinforcement, maybe I just want to see what the capacity is of my design cuts, we would use investigate sections. If I want the program to design the design cuts, I could design the sections. So there's two options here. I don't have any base reinforcement, so investigating maybe doesn't make sense. We'll go ahead and design the sections. And this takes just a moment of time to get through the design. Depending on how many nodes you have and the number of combinations, that really dictates how much time it may take to process the design of the sections. That's completed. And now we can really get into the results of the design cuts. So again, under analysis, I'm just going to pull up a strength combination. Let's do strength dead and live, for example. There's this option for design sections. So we can show deformation on the design sections. Let me go back to service total to check that. So under deformation, this will show me the deflection per span based on, and it colorizes whether it's okay or not okay. So here you see everything is green. Well, the span deflection ratio limit that we're checking against is displayed as L/360. If this passes, it'll show green. If it doesn't pass, it'll show pink. Some of these results are actually, they don't really apply, and I'll explain. So when we calculate this strip deformation, we take the maximum integrated deformation on any design cut divided by the span length. So here the span length is from 0.1, there's 0.1 to 0.2. So that's truly a span. And this is a legitimate, accurate number for that check along that span and that design strip. If I go to my middle strips, like this one, I was a little bit sloppy in how I modeled that. So here I actually have 0.1 and 0.2. So now my span is being defined as this entire length, when in reality, the middle strip probably should have been broken into points, additional points. So I probably should have broken this into 0.1, 2, 3, 4, 5, 6. And then I would have had a value at each one of those spans. So this is checking the maximum deflection on any of these lines based on the total length of that strip. So that result may not be as accurate in this case. It's really dependent on how you enter the support lines. And then finally, we have a span way over here. This span really is this distance here. So this distance L, based, if you take L over 0.18, that gives us this L/337. Because this is a cantilever, technically you could probably take that L divided or multiplied by 2 over 0.18. So this really is not necessarily an issue. It's just how it's checked, where we don't actually double the length of the cantilever. We just use the straight up calculated measured length between this 0.1 and this 0.2 here. Okay, let's go ahead and come back over to design sections. Turn that off. You can look at any type of action. These are our bending moments at service level. In the X direction, we could always toggle to Y direction and review those moments. Axial forces, shear forces. So any of these actions can be reported graphically. More interestingly, we get into stresses. This is basically void. We don't produce the stress cut values for RC slabs. This would be applicable only to PT. So we'll ignore that. Balance loading is applicable to PT. Let's go to investigation. This allows the user to produce the bending diagram or the bending capacities for given design. Let me see what's going on here. I think I may have a Yeah, do you see this spike right there? Something's going on where this is probably cutting into this opening. So this is causing a huge range in terms of value. So all of the other values are flat. We can't really see those. So what I'm going to do here, just so we can go back and actually look at values, let me turn this off just for a moment. I'll turn that result off. I'm going to delete the design strips out, and let me see if I can add a splitter there. Okay, and then I'll redesign the cuts. Just get a new updated result here. Hopefully this works itself out in terms of that value that obviously did not look right. We'll come back to analysis investigation. Maybe another location here that I'm missing. Let's see. Yeah, there's some other location where it's not doing what I would like it to do. So I'm going to, let me go back and delete one more time. What I'll do here is just use this one strip. I'm going to use two strips. I'll use this beam strip and this two-way slab strip. So I apologize. Let me go back and redesign this set of cuts. If I select only a group of strips, it will only design that one group. So now you see some capacities here. These look, yeah, these look very, very high. Let me try one other strip before we abandon this example, and I will show you in a different model because I want to be able to show this information. This is what I get for using an internal version that may be unstable. Okay, this is better. So along this strip, you can see the blue and the green. The blue is the positive or the negative capacity. The green is the positive capacity. So this really just indicates at any given cut location what that capacity is, and it also indicates what the demand moments are and what the demand capacity ratio is. You could also show this with demand. The gray line is the demand envelope. So for strength combinations, we produce this demand envelope. We can see, for example, in this span right here, there's this huge gap between the positive capacity and the actual demand. That just indicates that minimum reinforcement is likely controlling in the positive bending zone. Even in the negative bending zone here, minimum rebar would be controlling. And that could really bear itself out if we go back and look at the individual design cut value. If I double click on that cut and I go into a design section result, you can see this gives information about that cut, and this 2.7 square inches is predicated. It's dictated by the service total case, which is really just the minimum reinforcement. Where you have the demand graph kind of stacking on the capacity graph right here, this would indicate that strength is controlling. So if you double click there, you can see strength controls that location, and you can again produce information for that section cut. You could also graphically look at reinforcement. So for service total, if I want to look at the calculated reinforcement graph, this just shows me the bottom reinforcement and top reinforcement in area of steel. You could also produce that in for provided reinforcement. So this gives me a warning. If I select calculated, I have to go and generate the reinforcement plan before it can actually produce that graph. That's fine. I'll go to calculated plan. This calculates a reinforcement for this strip. I'll generate the reinforcement for service total. Okay, and now I can switch this over to the provided. So we have required versus provided. This is the amount of reinforcement based on the provided steel in the section. You could also do that for base reinforcement and also for in terms of an area of steel per the cross-sectional area in the section. Finally, if we we wanted to export the result. Now here I had obviously issues with some of the results there for this slab, but if I generate the rebar for the envelope of the slab, and we've only designed one section here, but I could always export this out under reports. I could export this to CAD, so I could generate a CAD file of this reinforcement. Before you export, you may want to clean the reinforcement up, and you can always double click on any reinforcement, modify its properties. I could manually adjust the placement. I could actually rotate that. The program automatically updates the required area of steel when we make graphical modifications to the rebar. So we can export as a DWG based on whatever is shown within the slab, or we could export this back to Revit. So if I go to File and I export this IMP, I'm going to use the latest IMP version here. And we'll say to Revit. Okay, and you'll notice there's a Revit option. You say, well, why didn't I use this option? This is really for legacy versions of the link, which is maybe version 2015 and prior to that. So we're using this latest IMP, which is later versions of the Revit link. I'll come back into Revit. I'm going to go to my structural plan that I'm working on, and I could import reinforcement for this slab that I created inside of Adapt. There's some issue here. I have to go through that. So anyway, ideally, if we import that, we could import tendons and also reinforcement into this slab based on the IMP export. So I appreciate, that's really all we're going to cover in this training. Next week we have a similar training to this. It's actually a repeat of this training for those that are unable to make today's date. If you are scheduled to be included in that training, feel free to enter. Again, we'll add this one to our YouTube channel. But if any of you have questions, please go ahead now, and you could write those questions into chat. There's already a few in queue, but I appreciate everyone's attendance and sitting through the webinar today. Hope everyone's safe and healthy. And if you have any questions outside of the webinar, again, please contact support@adaptsoft.com. Thank you. I'll go ahead and go right into questions. So the first question, when you put a rebar mesh in the model and calculate the rebar needed with calculate rebar plan, are those bars additional to the mesh? The answer to that is yes. If there's a need for additional reinforcement and the base reinforcement is not enough, then the program would add additional rebar to meet either minimum or strength requirements if the base rebar doesn't cover that. The next question, what's the difference between design the sections and investigate? I think I had answered that in the content of the training. So I read your mind, Karina, thank you. Next question, can you give a quick demo on how to obtain the crack deflections? Yes, sorry about that, Yusuf, I'll go ahead and do that. Let me come back to this. Now, this won't be complete only because I've had issues with the solution in this case. Once you design the reinforcement, once I run through the design of the sections, then in fact, let me just go through the process, even though we're having some issues here with the results. If I go ahead and design those design cuts, then after that, the option to calculate crack deflection becomes enabled. So we could go back to analysis, crack deflection. It's really just a post process beyond just the general analysis and the design of the cuts. And we can go through and design those cuts. The program reruns the general frame analysis with the new updated stiffness properties of the elements. And in terms of results for crack deflection, we have a couple of things that we can show. We can go back here to the loads, and you'll notice that under crack deflection, the program creates a solution for the uncracked version of that combination using iGross, and it also then creates a solution for the actual crack deflection. So this iGross might be taken down, let's say, to iEffective. That stiffness value is then used maybe for the nodes at each element, beam and shell elements. We resolve, and this is the outcome. So if we look at the sustained deflection, let me go back here to slab deflection. You can see we have a result. This is just, again, the elastic immediate deflection due to sustained load using I gross. But if I switch this now to cracked, these values, you can see this area, there's some cracking. It went from 0.4 to 0.46. If you want more relevant information on, well, what is the extent of the cracking? What's the loss of stiffness there? We can, for any cracked deflection combination for the cracked solution, we can go over here to actions and produce the reduced rotational stiffness. This is bending about X. You can see there's a loss of stiffness here from 1 down here. It says 0. That may be just due to the issues I was having, and that's dependent, you know, with each other in terms of the outcome of the reinforcement and the cracking. So this is the reduced stiffness about the y-axis, so bending about y. You can see, for example, at this beam location, we're losing roughly half of the stiffness there due to cracking. And that's how you can check the loss of stiffness. You can also check crack widths along the Y strips and along the X strips. So the crack widths are actually related to the service combination. So if let me collapse this, I'll come back to service sustained, for example. If I go down here to cracks along the Y direction, this shows me the crack width. So maybe we want some more accuracy there. I'll change this to 4 in terms of the significant digits. These are the crack widths along the, along the Y direction. So this along the Y would be relevant to bending about the Y, and then switching that to the other direction. This is along the X direction, or bending about the X axis. And these are, again, the crack widths. Question, can we import load combinations from ETABS? The answer is yes. There's a tool that's called the integration console. Let me see if I can find that here. I don't have it. Let me go ahead and show you here. Okay, so we have the integration console, and this integration console allows you to basically source an ETABS file, use their API. We extract information through this dialog, through this program and this interface, and then that writes an IMP file for entry into Builder. We would do the same thing. We would import, and maybe I want to create a new model, right? And if I create a new model, I would then import using IMP. The IMP file was written from the ETABS integration console, and you could import not only combinations, I could import entire ETABS models as well as solved reactions in ETABS. So an example of this would be if you have a transfer slab, this might be post-tensioned, and then you have a RC structure above that's analyzed in ETABS. Maybe I need to get these reactions at this level down to this mat or this transfer that might be post-tensioned. And so we can import this set of reactions and apply it into ADAPT from ETABS, and then carry on with the PT design for this transfer within ETABS, or within ADAPT rather. So that's how that's the intended purpose for the integration console. All right. Any other questions? Okay. Well, I appreciate, again, everyone's time. We're going to go ahead and conclude. Everyone be safe, and thanks again for joining today's webinar. Thank you.